Dear students, let us start our discussion with simply connected region. And simply connected regions or domain in a complex plane is a domain such that every simple closed path in D encloses only the points of D. Simply closed path means any closed path which doesn't cross itself. So this is not a simply closed path because it crosses itself. So this is simply closed path. This is not a simply closed path. So now simply connected region. Suppose this is region 1. So the region 1 is called simply connected region because if we draw any closed contour, closed path inside this region, then all the points within this closed contour are part of the region 1. So it is a simply connected region. So again, here if we draw a closed contour, draw number of closed contour, then points within these closed contour are also part of the region R2. Then this R2 region is called simply connected region. Suppose this region is R3. R3 region is this annular region. In this region, if we draw a closed contour like this, then this region lie within the closed contour, this C, but this region is not part of the region R3. So such type of region is called multiply connected regions. Here particularly it is called doubly connected region. Similarly here, if we draw a closed contour like this, so point here and point here are enclosed by the closed contour C, but these points are not part of the region R3. So hence it is not a simply connected region. A domain that is not a simply connected region is multiply connected. So it is doubly connected, it is triply connected, but not simply connected region. Next is Cauchy integral theorem, and Cauchy integral theorem is a fundamental theorem of complex analysis. According to this theorem, if fz is an analytic function at all points of a simply connected regions in a complex plane, and if C is a closed contour within the region, then closed line integral of a function fz along any closed contour will be equal to 0. If function is, and suppose here we have a complex plane, if we have a closed contour this, if fz is any analytic function, so its integration along this closed contour will be equal to 0 if function is analytic within this contour for all the points. Okay, for example, this e raised to power z. E raised to power z is the entire function. So this function is analytic throughout the complex plane. So if we draw any closed contour and take integration of this function along the closed contour, that according to this theorem will be equal to 0. Similarly, cos of z is also entire function. So according to this theorem, this integration must be equal to 0. Z raised to power n, or for z raised to power n also, where n is equal to 0, 1 and so on. This is also entire function, means fz equal to z raised to power n will be equal to analytic function. So z raised to power n is analytic function within this contour. So integration will be equal to 0. Now here fz is 1 upon z square plus 4. If fz is 1 upon z square plus 4, so z square plus 4 equal to 0. So z equal to plus minus 2 iota. These are the singular point. So in a complex plane, here like 2 iota, here minus 2 iota. These are the singular point. Singular point means function is not analytic at these 2 point. So but if C is a unit circle means radius of unit 1, radius equal to 1 of this circle. So these 2 points lie outside this circle. So within this circle function is analytic, because there is no point where function is not analytic within this function. Then we can say, according to Cauchy integral theorem, this integration will be equal to 0, okay, within this circle of unit radius. Next, let us prove it. Prove Cauchy integral theorem. So fz is u plus iota v. We can write it like this, and partial derivative of u and v are continuous. So let us take closed line integration of a function fz which is analytic within this contour. So we have substitute value of f and dz is dx plus iota dy. So we solve it, we get it. Now we will solve these two integral using the Stokes theorem. And Stokes theorem state that line integral a dot dl closed line integral will be equal to surface integral of curl of A. This surface integral, this is called Stokes theorem. So we have written Stokes theorem in this form. So now we will solve these two integral using Stokes theorem. And for first integral, Vx is equal to u and Vy is equal to minus v. We substitute value here, we will get this. For particularly this, we will get this. And similarly for second part, Vx is equal to v and Vy is equal to u. We substitute value here, value of Vy, Vx. Vy is equal to u and Vx is equal to v. Here we will get this. Now we know fz is an analytic function, so it must satisfy Cauchy Riemann conditions. We will substitute here Cauchy Riemann condition. So according to Cauchy Riemann condition, this must be equal to 0 and this also 0. So ultimately we will get this. So hence we have proved that closed line integral of analytic function is equal to 0.